Another beautiful day outside. Boy, I hope it lasts forever, doesn't it? That would be nice. So, as you're getting going on these notes here, why is it that garbage men do not really get trained for what they do? Why is it that garbage men don't really need training? What's that?
Because they're trash at it. I mean,
good guess. I like that answer.
What was the question again?
Question was, why is it that garbage men don't get training for what they do? Ella said because they're trash at it. I was just going to say they pick it up along the way. But either answer works just fine. What's the hardest part about skydiving? Oh, that would be very difficult. You'd only do it once then, I guess. Hardest part about skydiving is the ground. Yeah. That's deep. That is deep. So, in terms of momentum, just like in the energy section, we dealt with the conservation of energy. How you can set energy at the beginning equal to energy at the end, and use that to solve for all sorts of different things. The same thing is true with momentum. You can set momentum at the beginning equal to momentum at the end, and use that to solve for all sorts of different variables. So, this is kind of the main thing that we're looking at today, the conservation of momentum. Momentum at the beginning is equal to momentum at the end. Now, what I have under here, these are just some scenarios where you can make this equation even easier and more simple. Because if you would extrapolate this into its true form, and you've got, say, two objects, this, because, momentum is equal to mass times velocity, you'd have mv1 original plus mv2 original, that would go here, equals m1v1 final plus m2v2 final. So it's a long equation, but under some conditions you can make it much shorter, and that's the purpose of the blue and the red here. So scenario 1 would be if you have one object before and after hitting a wall. So under these conditions, we're just talking about one object. So if you've got any object at all, maybe it's a baseball and it hits a wall, or maybe it's a shark and it hits a wall, or maybe it's a ball of yarn and it hits a wall, maybe it's a tennis ball and it hits a wall, maybe it's a Rubik's Cube and it hits a wall, maybe it's a bouncy ball and it hits the wall, or maybe it's one of these special bouncy balls and it hits the wall. I was waiting for that to hit the camera. So, if those are your conditions and you've only got one object that you're dealing with, then the original momentum is just going to be the original momentum of that one object. And your final momentum is just the final momentum of that one object. And that means that your equation is just going to boil down to this. And I guess you don't even need the ones on there since you're just dealing with one object. But because the object was going, towards the wall in question, it went in that direction with a certain velocity. After it bounced off, it had that same velocity but in the opposite direction. So that's a quick way that you can do a problem like that. Now, if you've got one object being pushed or shot away from a second object, that makes this equation boil down to something easier as well. So let's say that you're out in space. And you're just floating around out there. And you just happen to have a bowling ball with you. Now you're floating around out in space. And you're floating around out in space like this. And you want to get back over there by the spaceship. And you don't have anything on your suit that's going to shoot you in that direction. But you do have a bowling ball. So what can you do with the bowling ball? Yes? Yeah. Take this bowling ball, throw it in that direction, and you're going to go flying off back towards your spaceship. And that's what this scenario is about. So that's like an example of something being pushed away. Let's say you use an example of something being shot away with this altimeter right here. It's like my favorite Christmas gift ever. I don't think they make them anymore because it looks like a terrorist weapon. So if you're out in space and you're just floating there and you launch this in one direction, you're going to start floating back the other way. Maybe there's a couple other reasons they don't make these anymore. So, those are the kinds of scenarios in which you would use this type of reasoning that I'm going to show you here. So if you're dealing with these two objects, original momentum and final momentum, if you're just floating in space, what is your original velocity? 0. If the object you're holding is just floating in space with you, what is its velocity originally? 0. So the original momentum of this would be nothing. So 0 m1 v1 plus m2 v2. Bless you. So then this would boil down to something similar to that. If I wanted to keep m1 v1 over here, you would just have a negative in there. And that negative could be on either one. It doesn't really matter. But yeah. So again, if you have a scenario where you just have one object, your momentum equation turns into something very easy to deal with. If you've got two objects and they both begin at rest, you can start with a similar looking equation. And the question would tell you whether or not the direction is, positive or negative. If it doesn't, then just assume that to the left would be negative and to the right would be positive. Because we do have to make sure we take our directions into account in this chapter. Velocity is a vector. Momentum is a vector. So those directions are going to matter here. Questions on any of this? Okay, so that's kind of the easier stuff. Let's get into scenarios where we cannot make this equation simpler. There are two kinds of collisions in momentum. There are bouncy collisions, where objects come together and they bounce right off each other, and there are collisions where they come together and they stick. So the type we're going to deal with first are the bouncy collisions. And I'll give you some time to draw this. Just to give you an idea of what's happening, we've got two individuals here, and they are in bumper cars. They are not hamburgers. And this guy is just a cruel individual. And he is going to the right at 5 meters per second. And he's going to try and hit this guy whose car doesn't really work. His original velocity is 0. And they're going to collide and bounce off of each other. We call these types of bouncy collisions elastic collisions. And we're going to use this setup to solve one of these problems. So take your time setting this up and we'll go through it together. Makes you wonder what else is under my table here, doesn't it? Okay, so let's take a look at this again. So we've got this guy who is just bitter and angry for some reason, and he's eyeing up this poor individual. He's going to smash into him, and he's going to have an elastic collision with him. They're going to bounce off of each other. So that's our setup, and the thing that we want to find out ultimately in this problem is what is going to happen to this guy right here. We know after the collision that the first guy who made the collision is going to move off at -1 meter per second. So if he's moving to the right at +5, and after the collision he's moving at -1, that means that he's now moving to the left at that speed. So given that information, the question is then, how fast is this guy going to be going after the collision? And that's what we want to try and solve for here. So you can see the equation, and this is on your formula sheet too. When you're dealing with bouncy collisions, this is what you have to use. It's just your conservation of momentum equation spelled out a little bit longer. So original momentum equals final momentum, and because we're dealing with two objects, we have to take the original and final momentum of both of those into account, and that's where this equation comes from. So the only thing we're trying to find is this right here, the velocity of the second object. So all I'm going to do is just try and get all the letters away from velocity 2, and I'm going to go ahead and plug the actual numbers in once we get it to that point. But you could throw the numbers in right now if that's something you wanted to do. So let's see here. If I want to solve for that V2, I got to move this product over to the left, and that's going to make it negative. And then that would be equal to M2V2. So obviously, in order to finish this up, I have to divide both sides by that second mass. Once you do that, now you've got an equation that's going to solve for that velocity. So it's just a matter of plugging the numbers in then. Of course, you could have dropped this off right away if you wanted to, because that original velocity of the second object is equal to 0. But yeah, if you write it all out, that's what we would have. And once you do that math, you should end up with 9 meters per second. Questions on this? So yeah, even though you have a long equation, you're going to know everything except one variable. So you just do a little bit of math to get there. All right, so that's the start of this. And as exciting as this was, there's a sequel to it. And this is called Nice Guy's Revenge. This is where things really get intense. I'm going to warn you. Notice now two things. Number one, the nice guy got his car working. Good for him. The mean guy is still a jerk, and he's still moving towards that guy with his 5 meters per second. But notice that they have removed the bumpers from their bumper cars. So what this means is that when they collide, they will have a sticky collision. Those cars will come together and they will crumple and smash together as one mass. We call those inelastic collisions. So the question here is going to be, who wins in this battle? Does this guy get his revenge, or does he come out on top again? So the way we would figure that then is, there's a new equation here that we'll go through together, but actually I'll just give you some time to draw this, and then we'll talk more in a second.
What happened if you had like one that had a bumper and then one that didn't?
Depends on how good the bumper was. If it's a weak little thing, you'd probably have an inelastic collision, but if it's still a good solid bumper, you'd probably bounce off. As a bit of a disclaimer, this does not mean that I'm advocating that you and your enemies go to Six Flags and settle your differences by removing bumpers off the bumper cars. That being said, that's what these two guys do. And so the question is, who do you think wins this battle? And the way we would determine that is, after they collide, there's just going to be one mass of wreckage after they do so. So the question is, what direction does that wreckage go after that collision? If it moves off to the left, then this guy will have gotten his revenge. If it moves off to the right, the original direction that guy was going, then he gets the better twice in a row there. So you can see kind of the little conundrum here. This guy weighs a lot less, but he's moving much faster to the left. This guy weighs more, but he's moving slower. So, who do you think is going to win this battle? The jerk or the nice guy? You got 1 vote, 2 votes for the jerk. Anybody want to side with Mr. Good Guy here? We got 1 for Brian. Okay, and Caroline? Oh, a couple more. All right, so let's take a look and see what happens here. So for these inelastic collisions, you'll notice the equation looks a little bit different. We're still starting with this, original momentum equals final momentum. The only difference is here, we start with 2 objects, but after they collide and stick together, we really just end with 1. That's why there's only 1 momentum on that side of the equation. So that's going to come down to this then. The left side of the equation is going to look the same as the first time we did this, but the right side is different. The reason for that is because you just have 1 mass, 1 object that's moving after this type of a collision. And that's where this comes from then. So, if I want to solve for that velocity, This should be pretty straightforward. We just got to divide both sides by the sum of those two masses. And that's exactly what we're going to do. Can somebody plug this into their calculator? Find out the results of our matchup. Yes?
How did you get 300 plus 500?
So this is the, oh, yep, that's my mistake. This is a 200. Thank you for catching that. Yeah, mass 2 is 200 kilograms, yep. Negative 0.2 sounds right on the money. So who won the battle? The nice guy did, because he was originally moving in the negative direction, and that is the direction the wreckage is going to be moving after this intense collision. Questions on this?
Is it always the person with the higher velocity, or does it sometimes use heavier?
Yeah, it depends. You know, basically what it comes down to is whichever of these two guys has the greater momentum, that's the direction the wreckage is going to go. So 8 times 200 turns out to be a little bit higher than 5 times 300, and that's why he wins by a little bit. Okay, so we just have one extra little place to go after this, and that has to deal with impulse. We talked about impulse a little bit yesterday. I'd like to go into greater depth on that today. Most of the stuff you need for impulse is listed right on your formula sheet in the momentum box. So impulse is equal to all kinds of things on the bottom of that. It's equal to force times time. It's equal to change in momentum. And one extra thing that's on that I didn't mention yesterday has to do with if you would find a graph. If you have a force versus time graph, and maybe it looks something like this, if you would calculate the area of this right here that's trapped by the curve, that would also be equal to impulse. That's also written on your formula sheet. I just wanted to show it to you real quick. So there's all kinds of ways to figure out your impulse. You can find it graphically. It's equal to change in momentum, and it's equal to force times time. There's all kinds of ways to figure this value out. So, one thing that you do need to make sure you're very well aware of is if you have two objects and you can find the impulse or the change in momentum of one of those objects, that's automatically equal to the impulse of the second object, except it's going in the opposite direction. So it would be negative. So if you have enough numbers, if you have enough information to find your change in momentum of one object, then the second object that's involved in that collision, you know what its change in momentum is equal to. We'll go through an example of this right now. What's that look like?
Pumpkin.
Hey, all right. Most of the times these look nothing like what I want them to look like. Okay, so we're going to say this is a pumpkin. And we know all sorts of things about this pumpkin. We know its mass. That's 2 kilograms. We know it's going to start. I'll put a little P for pumpkin. The original velocity of this pumpkin is 0. It's going to start at rest. The final velocity of this pumpkin is going to be equal to 0.9. Why does this pumpkin start moving, you ask? Well, because you don't like Halloween. So you take a pellet gun and you hit it with a little pellet. So the bullet is going to move through the pumpkin. It's going to come out the other side. And using just the information that we have about this pumpkin, along with a few more things I'm going to give you about the bullet, we can find all kinds of interesting information. So we're going to say this bullet has a really small mass. We'll say it's 10 grams. And we'll say that once it exits the pumpkin, it has a final velocity, use B for bullet, of 100 meters per second. So that's the final velocity of the bullet there. So that leaves really just one thing that we would need to solve for in terms of the information here. We know everything there is to know about the pumpkin. We know the mass of the bullet. We know its final velocity when it exits. But we're not given the original velocity of the bullet. And we're going to use impulse in order to figure it out. So let's see what we can do here. What color should I use?
Blue.
All right, we'll use blue and we'll use black for this one. So let's use blue for the pumpkin. We know all sorts of things about the pumpkin here. We know the mass and we know the two velocities. Therefore, we know what the impulse is going to be. Because impulse of the pumpkin is simply equal to its change in momentum. This means change in momentum of the pumpkin. So these P's mean different things here. So I want to figure out what that change in momentum is going to be. And change in just means final minus original, and we can plug those numbers in. So that's our value for the impulse of the pumpkin. And as I mentioned before, if we know the impulse of one object in a collision, we automatically know the impulse of the second one. What's the impulse of the bullet going to be?
Negative.
Yeah, negative 1.8. So when we use this information to find things out about the bullet, we know that we can start with the change in momentum, or the impulse of the bullet, being equal to negative 1.8. So I'm going to leave this out just for now because I want to do it with the letters, and I'll put the numbers in later. But we do have the impulse of the bullet. We have that value. So that's just going to be equal to change in momentum. So if what we're trying to solve for is the original velocity of the bullet, we just got to get that variable all by itself. So I'm going to move mv over to the left. And that makes the MBVB negative when I move it over there. And in order to finish up and solve for that original velocity of the bullet, got to divide both sides by negative mass of the bullet. Let's do it this way. And that cancels out this. And we can plug those numbers in then. So, once again, the impulse of the bullet is going to be negative 1.8. Mass of the bullet is 10 grams, but we need that in kilograms. Any idea what that conversion is going to give us? Close. Just 1 0. Yep. 0.01. So that's what our mass would be in kilograms. Final velocity of the bullet is 100. And then we divide all of this by the negative mass of the bullet, which again is 0.01. And out pops our final answer. Did somebody find this out already? $280 is right on the money. And that's exactly how we would solve a question like that. We have to acknowledge that if we have enough information to find the change in momentum or the impulse of one object, that will directly apply to the impulse of the second object. So if the impulse of the pumpkin is 1.8, that means the impulse of the bullet is going to be negative 1.8. And we know the rest of these variables except the one we're looking for right there. And we can figure that out easy enough. Questions on this? Okay, so the last thing I just want to mention here with regards to this is if I mentioned it like this because sometimes you'll specifically be given information about impulse. But even if you're not, you can use this information to just solve this by using the conservation of momentum by itself. Let me show you what I mean, and then we'll call it a day. You can solve just about every single question in this section by starting right here. And this is no exception. Even if I don't, know in my mind that I can find the impulse of the pumpkin, that naturally is actually going to just pop right out of that expression. Because it would look like this. If you just start with this long conservation of momentum equation, you know every single one of these letters except this one right here. Wait, no. This one right here. Because we know the masses, so we know all four of those. We know the original velocity of the pumpkin, that's 0. We know the final velocity of the bullet, that's 100. We know the final velocity of the pumpkin, that's 0.9. So you could just plug that into the long momentum equation and be on your merry way there. Either way works just fine. Questions on any of this? Okay. Kind of makes me wish it was Halloween.